did my engineering from Chennai, and the first few phrases in Tamil that my friends taught me, I cannot say them on stage here, but kunju kunju Tamil theriyum. And we can start the presentation. We have the PPT. So it's an absolute honor to be here in Coimbatore. We did our first project in 2014, and since then we have been coming back here. I love the weather, love the food, and people are an absolute gem. Gentlemen, and thank you, sir, Shastri sir, for appreciating our work and for the beautiful presentation. You have really set the tone. Hearing you speak was like I am speaking. It felt, a person with a lot of experience, profound experiences talking. That is what came across in your presentation. So thank you for that. All right. So yeah, next one. This one, right? All right, so I'll be talking about three major elements: earthwork, design, and joints. And this is actually what I think about 90% of the times. If we get this right in our project, then it's bound to be a success. Earthwork, as all of you very well know, you can spend a fortune on your floor, but if your earthwork is poor and it settles, your floor is no good. Joints are actually the weakest element of a floor, so you need to take a lot of care while designing your joints, because that's the biggest pain point. Design obviously is the first aspect of any civil engineering structure. So first section, earthwork, I'll look at some basic concepts, help you visualize soil as a spring. You look at plate load test. That is the most common test we use to test a subgrade. We'll talk about subgrade, compaction, subbase, and construction of subbase. Okay, so fairly basic stuff. Earthwork has basically two components, a subgrade and subbase. Subgrade is something, your cheapest material that you fill your building with. Let's say you're building a warehouse that is about 4 foot high from your road level. About 3 feet you fill with good earth. It might be actually available at the site itself, or you bring it from some source. Second is a base or a subbase. That is what you see in the picture here. That's the layer about 6 inches, 8 inches, 10 inches, depending on the design, that comes on the subgrade. So it protects the subgrade from overstressing, because subbase is a stronger material or has more strength than the subbase. When you're talking about roads, it actually acts as a filter media for water. And most importantly, when you're talking about flooring, it holds construction traffic, because you're having a lot of concrete trucks moving on these subbase. So you need to have a subbase that can withhold that sort of traffic. Again, fairly basic stuff. This is the process. You bring earth, you dump it, you level it with a motor grader or even a JCB, and then finally you compact it. What is important is to have constant sprinkling of water, because that is what takes you to your optimum density. And then finally, and most important, you test it. So we'll take a step back. Actually, a lot of soil engineering or concepts of earthwork that we use in flooring are actually derived from highway engineering. And there are two kinds of roads that all of us are aware of. One is a flexible pavement or a bitumen pavement. The other one is a rigid pavement or a concrete pavement. The design principles of both of these are different, so we'll go over both of them. And both of them have value when it comes to flooring. Very simple illustration. So this guy is sitting on a bunch of mattresses. He weighs about 60 kgs. So the yellow line that you see, it has higher pressure. And as the weight goes down, it disperses itself at an angle of about 45 to 60 degrees. So when you go down, the pressure is actually 1/3. So what this means is you can have a weaker material lower down, but you need a stronger material up there. So if you look at the left side, we have bitumen at the top, you have a base, you have a subbase, and you have a subgrade. So now the important point to notice, if you have a weaker subgrade, if you have a weak soil, you need a thicker subbase. This actually lends, we use this concept in designing subbases for floors. Okay, now if you talk about rigid pavements or a slab action, this is applicable to a building as well. This is a cot which we see in our houses. The posts are actually columns. Then you have the beams on the four sides, and then you have the slab in the middle. And you see this guy, sitting on that cot. You can actually see the tension, the profile there. There is tension in the slab. Now, how do we extend this to flooring? The same cot, but now imagine this cot has infinite legs. This is how it looks like, the second picture. So the principle of doing a floor design or a floor slab design is you imagine a slab which has infinite amount of supports, and then you have, and then this slab is also exposed to bending moments, sagging and hogging. And this is actually what we call as Westergaard's model for rigid pavement design. Okay, now I'll just take you back to your physics class. So this is a spring. The first one is an unloaded spring. You apply a force F on the spring. It extends by a distance x or displaces itself by distance x. If you increase the force by 3 times, it displaces itself by 3 times. So there is a linear relationship. Just think of it as a rubber band. You stretch it by a certain force, you put some force and it stretches itself, you release it, it comes back. Now why I'm showing you all this is because the design of a floor, we actually simplify the soil or the earthwork as a spring. So when you think of soil or earthwork, think of it as a set of springs. Now what you want is a harder spring. The softer the spring, either you will have settlement or you will have a thicker slab which has more reinforcement, higher grade or thicker, more thickness. So now how do you go about determining the K value? And if all this sounded complicated, so this is just, look at this image. A soft mattress is a soft spring. That means a subgrade that is weaker or softer. A hard mattress is good soil, harder, which deflects or compresses less on pressure. So you want a hard mattress, not a soft one for your subgrade or your subbase or your earthwork. Just a very simple image to drive home the point. Okay, now on field, how do you know that the soil at your site is a hard mattress or a soft mattress? What you do is a plate load test. This is the most common and most preferred test that we use. So again, visualizing your soil as a spring, this is how it looks like, the apparatus, and this is how it looks like on the site. So what we have here is a jack. We have a set of plates, we have jack, and then we have a counterweight. With that counterweight, we are able to apply force on the earth, and then we note by applying constant pressure or increasing the pressure or force, how much is the earth or the soil compressing or getting displaced. So this is how a typical result or a test looks like. On the x-axis is the pressure that we are applying. On the y-axis is the settlement. So you notice to get to a settlement of 2 mm, we had to apply a pressure of about 40 tons per square meter. That is actually a lot of load. So this turned out to be a good subgrade to build a floor on. And typically our cutoff point is 1.25 mm. So whatever the load is at 1.25 mm settlement, that is what we use to calculate the K value or the spring constant. Now CBR is also commonly used for road work. That is actually the standard for bituminous roads. But we try to avoid that when it comes to floors, because CBR is a material property test and it doesn't actually test the compaction that you're doing at site. So you're better off doing a plate load test and a combination of Proctor density. I'll go over that also in a different slide. But if you are doing CBR, this is a good reference. So as a K value, what we are looking at, if you look at the y-axis, we are targeting a minimum value of 0.05. That translates to a CBR of about 10. So what you should safely be looking at is a CBR between 10 and 20. It gives you a K value of about 0.05 to 0.08. But it is better to do the plate load test instead of going for CBR. Okay. Alright, so now we look at major types of soils. Now there are, there is a million kinds of soils, but these are the 4 broad classifications: gravel, sand, silt and clay. a good soil for earthwork actually has a combination of all these 4. We do not want just one, and I will explain you why that is. If you look at the points to consider, grading, drainage, volumetric change and cohesion. Grading, so gravel is the coarsest, then comes sand, silt is finer and clay is the finest. So you need, like we do in concrete, right? We grade from 20 mm down to 150 mm or 75 microns. This is what you need in your soil also. You need to start with gravel and end at a little bit of clay. You need clay. I will explain you why you need a little bit of clay. Drainage, gravel and sand are very good in drainage. Silt not so much. Clay obviously we know is very poor in drainage. So that is an advantage of gravel and sand, because you need good drainage. Volumetric change, silt and clay is very poor, because silt not so much, clay definitely, because with water they expand, and as it dries, it shrinks. That is what you see in the picture. The clay is kind of cracked because it is dry. Cohesion, this is the advantage of having silt and clay. It is like a glue. Silt and clay is cohesive. So now what you end up with, when you mix all these, what silt and clay gives you is the cohesion. It is like a glue that binds everything together. What gravel and sand gives you is the stability. So you actually need a little bit of all 4. Now this is a fairly commonly used soil classification. If you look at the bottom, on the left side it says gravel, then it says fine sand, then it says silty or clay, gravel and sand, and then it says silty soils and clay soils. So for us, the sweet spot is actually what I've circled. That is what I just described. You need silty or clay, gravel and sand. Predominantly gravel and sand with some amount of silt and clay is good. You definitely do not want silty soils or clay soils. And gravelly and fine sand would be unstable, because if you're driving any sort of construction traffic, your material will just keep moving around. Okay, a very important slide. How should we go about compacting? So what you see on the right side is what is fairly common. You kind of dump soil in lifts of about 1 meter. And what you end up with is, the first image I've shown is a roller, a vibro or a static roller. The white semicircle that you see is actually the bulb of influence. That is where your roller is able to exert any sort of influence. Below that, below the red line, it is actually not able to compact. So all the stuff below the red line is prone to settlement. The second image that you see is of a hydra or a crane. So what we commonly hear is that the PEB guy has been doing his work. He has been moving a lot of material. He has been moving a lot of, and that has kind of taken care of the compaction. But that is not the case. Similar to the road roller, the hydra or the crane also has a bulb of influence, which is much lower than a roller. Third and the most important thing for you to note is, when you do the test, your test is also going to pass, because the test also has a bulb of influence. Your plate load test will test maybe 300, 400, 450 meters. So this is very common, right? And you do all your tests are passing. But then why are you seeing settlement at site? 2 reasons, because eventually, even the guy is rolling it knows that if you just test the final layer. Nobody bothers to test when you're kind of lifting the layers. And final layers is bound to pass, but then your earthwork is bound to fail because of these reasons. Now, how you should actually go about it is just limit your lifts to about 250 to 300 mm. Roll it preferably with a vibro roller. Also test every layer. So a plate load test might, cost more and take more time, but what you can actually do is use a Proctor test for all your, intermediate layers. A 95-98% Proctor test, you could actually just use a rapid carbide test at site. You can train 2 of your guys. You do not need to actually involve a geotech consultant, because that kind of slows down, right? The guy will test, will make a report, take a week. You can, 2 unskilled guys can do that rapid moisture test at site. It's like a 4,000 rupee kit, and then that can save you a lot of trouble later. So the points to consider: the lift height, we already discussed 250 to 300 mm layers. Type of roller, vibratory. If it's clay, sheepfoot roller, that is not very common in India. Watering, very important. Too much watering is also detrimental, so balance depending on the type of soil. Testing type, Good to do plate load, and combination of plate load and proctor, better to avoid CBR. Testing frequency, there are codes that talk about it. Typically plate load is one test 1000 square meters. Walls and columns should use a baby roller. We use the most common thing is to use a plate compactor. Again, it limits the compaction to 4 inches, but a baby roller, you can have a larger bulb of influence. Okay, so now what do you do if you're in a situation where the soil is poor? The best thing to do is, so you have two options: either you replace the soil or you stabilize it. Replacement is the best. You just get rid of the poor soil. That is the first, that is the ideal. Just replace everything, get rid of it. If for whatever reason it is not possible, at least replace at least 1 or 2 feet. Because again, the first slide that I said, as you go lower, the load disperses, and then you have lesser pressure or force on the poorer soil. If it is extremely poor, do a deep excavation. Soil stabilization, you could use lime, cement, fly ash. Two places where we have experience. We have worked across 15 states in the country, and we have dealt with lots of materials, and Kolkata and Vijayawada stand out in poor soils, and Shastri sir also mentioned Gujarat. Calcutta, they tried to mix fly ash, and the floor settled horribly. Like, we didn't do the floor, but they had about 200 mm settlement in the floor. So that is what poor soil or poor soil stabilization can do to you. Vijayawada is similar, black cotton. Now, what are the major types of subbase? The first picture is GSB, granular subbase, water-bound macadam or water mix macadam. This is something that is most commonly used, and this is what we also recommend, and I will explain you why. Second type is plain cement concrete, PCC. Third is Muram. In Hyderabad, actually 90% of our projects we've actually done on Muram, because quality of Muram there is excellent. So, you should have that awareness. It's a very, very city specific. These materials are very, very city specific. So you need to know what is good there. So, in a place like Hyderabad, the GSB is really unnecessary for a warehouse project. So done many projects just on Muram, very good quality. And this is a special case where you have cold storage, you have actually puff panels. So then you need to design everything accordingly. What are the points to consider? Obviously, fairly simple: cost, time, K value, which is the hardest, which is the most hard spring of all these. So PCC is, but there is limitation of PCC also, which I'll talk about. And construction traffic, it should be able to hold construction traffic, and rectification. Okay, so I'll leave this to you to answer how granular should the subbase be. The first picture is clearly crazy. I don't know how they will be able to fill the voids. These are actually pictures I've taken from sites I have been to. Nothing in this presentation, by the way, is from the internet. It's all pictures of our work and sites I've been to. You can actually, as sir mentioned, that you can actually refer moth specifications for gradation. So just a summary of subbase construction: use a vibro roller or a static 8-ton roller. Baby roller is advisable for edges. 98% dry density is the target, 95% would be the lower cutoff. Your target subbase levels, obviously you cannot have a 0-0 floor, and you cannot have a 0-0 subbase also. So reasonable specification to give to the earthwork contractor would be 0 to -15. The reason we say 0 is because we are designing for a certain thickness of slab, and we need that 150. That 150 can become 160, but it should not become 130 or 140. So we don't look at an average thickness, we look at a minimum thickness. This is a very important point. If the client is insisting, I just want to spend this much, then it has to be clearly communicated that we are talking about average thickness and not minimum thickness. The surface should be free from steps, ruts, depressions, voids. It should be like a smooth flowing surface, because anywhere you have step in the subbase, you're gonna have a reflective crack in the floor. So if you have that situation, you have to break your panel, put an armored joint or some sort of a construction joint so that your concrete can move independently on both sides. Sand should only be used to close the open surface and voids. Sand should not be used as a blinding layer. There have been situations where people have put like 2 inches, 3 inches sand as a topping. You should never do that. Typical layers of GSB is 100 to 150 mm thickness. Okay, I spoke about PCC. Now, first thing, PCC cannot make up for poor compaction of earthwork. It's like, pigeon closes his eyes when a cat comes, it's the same situation. PCC is not going to save you poor compaction woes. Biggest disadvantage of PCC is no cutting or filling is possible once it is laid. So what we do typically is, before constructing a slab, we actually check levels at every 3 or 4 meters, and wherever there's a high spot, we cut the high spot. Wherever there's a low spot, we fill it with a low spot. That is very easy to do with a WMM, WBM, GSB or Muram. That is not possible with PCC. Once you're done with PCC, you're done. You cannot scrape it, or, I mean, you can do, but it's gonna cost you a bomb and waste a lot of time. So what can happen is slab thickness can be compromised at high spots, or wastage of concrete can happen at low spots. It is slower and expensive. But the biggest advantage of PCC is, which is important to share, is it gives you the highest K value. It is the stiffest spring you can manufacture. So where you have very heavy loads, sir talked about ASRS floors, clad racks, where you're talking about 20 ton, 30 ton point loads, there PCC gives you that extra support that your slab needs. So it's good to have there. So a very easy way to proof check your work is it should withhold construction traffic very well. If you see these two pictures, the tires or whatever it's running on the earthwork is barely leaving a mark. There's no ruts, there is no depressions, just barely leaving a mark on the earthwork. So then there is more to talk about. There are other tests, frequency of testing, how can you project sub-base K value from subgrade K value, and how to treat insulation puff boards. I can go for another hour, but I'll just move on to the next topic now. So now the section 2 would be I'll talk about design, go over the introductory material. Sub-base we've talked about, but I'll just put one slide. The key components of structural design are the concrete and the reinforcement, right? I'll talk about it briefly. Shishadri sir is going to talk about concrete, so I won't steal his thunder. I'll just keep a couple of slides here. Reinforcement, he's going to talk about SFRC flows also. Defining loads, very important. How do we define loads? Because this is where we miss a lot of times. Specifying levelness and flatness, again understanding why we need certain levelness and flatness. Concrete mix design, very important, because this is ultimately a concrete floor. And supply, this is what we do not think of often. How much concrete can you supply at that particular site consistently on a daily basis? Like, you should not be insisting on a 1,000 square meter panel where all you can get is 60 cubic meters of concrete. So all these factors need to be considered at the design stage. Subgrade and sub-base design, obviously I've talked a lot about it. Now when you put all 4 of these together, what you end up with is a joint and panel layout. So a joint and panel layout actually does not come about randomly. This is what you finally see at execution, but all this needs to be done properly to have the right joint and panel layout. Okay, a very, very simple way to visualize shrinkage, because all we think about as flooring guys is how do we minimize shrinkage, because shrinkage leads to a lot of problems. At the design stage, this is the basic element that any designer thinks about. What can he do to minimize shrinkage? And just to explain you shrinkage in a very simple manner, think of an orange peel. Like, if you leave an orange peel on the table, it shrinks, right? It loses water. This is what happens to concrete. The first image is concrete that is about 1 week old. This is concrete that is about 1 year old. It has lost water. It's gonna shrink. Your joints are going to open up. And your construction joints are already the weakest part of your building, and they are gonna open up even more. And the more a joint opens up, and then you have forklifts or material handling equipment moving on it, the more it is going to hit the joint and more it is going to break the joint. So lesser shrinkage, lesser joint opening, lesser joint damage. Very, very important when it comes to joint. And yeah, again, I've talked about sub-base enough. Just whenever you think of sub-base, think of a mattress. You don't want a soft mattress, you want a hard mattress. You don't want that guy sinking into the mattress. Concrete, I'll talk about practical stuff, not the theory, because I can't get into concrete mix design. That take half a day. A macro level, what we are dealing with in our country, hot weather conditions, obviously. There is extreme variation in raw material quality across the country. As I said, we have worked in more than 15 states. We see extreme variation in sand, cement, even admixtures. And unfortunately, flooring concrete has not caught the attention of the RMC suppliers. I don't know why that is, but we are not one of their core target clients. So they do not apply their resources to understand why and how flooring concrete is different from regular concrete, because it is different from your regular design mix. At the micro level, site conditions are far from ideal. We are in situations because of time pressure, as you rightly mentioned, open to sky casting, site is not ready, you're just forced to pour. Erratic supply rate, I'll show you slides, actual site data from one of our sites. It can vary anywhere from 10 to 24 cubic meters. I've seen about 3-4 sites in Canada, and their average rate is about 80 cubic meter per hour. So the scale is entirely different. Our average supply is about 15 cubic meter per hour. Their typical, so they do like a 8 hour shift. So they typically pour about 400 to 500 cubic meters a day. And if a pour is exceeding 100 cubic meters, I start to get nervous, because I know there's gonna be some breakdown or some failure at some point in time in the project, because above 100, 120, the consistency becomes a concern. Inconsistent concrete quality, significant slump variation. Within a day, you'll have like a 120 slump, you have a 180 slump, 150 slump. Which I already mentioned, concrete per day determines the panel size, and it is not the other way. You cannot force concrete to fit to your panel size. You have to fit your panel size to the concrete that is available. And having said this, I can speak for the whole flooring fraternity. We are facing all these challenges daily, but we are actually able to consistently deliver international quality projects. I'm not talking about myself, I'm talking about the whole flooring industry. Ganesh is sitting, I think Bhaskar is somewhere here, Muthu Senthil is here, so I'm speaking for everybody. And we have worked with international consultants, all of us, and we have got this regular consistent feedback, because despite all these challenges, we are doing very well, and our industry is self-sufficient. We are not dependent on any significant imports or any significant technologies. The industry has come to a stage where we are self-sufficient. It is kind of indigenous. Okay, sorry. Yeah, so this is site data from one of our sites. The green line that you see is the time. So the x-axis is the truck number, the y-axis the time of the day. So if you see the green line, that is when the batching started. So we started batching at 6 a.m. It ended at about 12. At site, we started at 7, ended at 1 p.m. Looks good when you see start and end, but then the devil is in the details. You see truck number 1 and 2 arrive at the site at the same time. Funnily, truck number 5 arrives before truck number 4. Then truck number 7, 8 and 9 arrive at the same time. What we need is, ideally we need one after the other. So what this does is, you can have slump loss, you can have cold joints. So this is something, again, you need to consider when you are on the design stage, at the design stage. Reinforcement, all of us are very familiar with this 8 mm 200 center to center. We have been doing for donkey's years. But what is important to think about is what position should the steel be in? Position at the bottom, you're obviously adding movement carrying capacity to the structural design. Top, the argument is you get crack control, but then the point to consider is you also have to saw cut the slab at 1/3 the depth. So if you have a 150 thick slab, you have to cut at 50, a 50 saw cut. Where do you put your steel? At 60, 70, you're at the neutral axis, where actually in the center the reinforcement is doing nothing. At the neutral axis, it is not adding any moment capacity. It is not offering any significant crack control, because if you need crack control, that is how we design seamless floors actually, where the top, where the steel is actually 25 to 30 mm from the top, but then a seamless floor by design does not have any saw cuts. And one limitation of reinforcement bars is the unreinforcement section is vulnerable. That is where steel fibers come in. Okay, so there are numerous types of steel fibers, types of fibers, steel, plastic, glass. Plastics is something that we have avoided because of finishing nightmares. A key feature of steel fibers is three-dimensional dispersion. That is the limitation of your torch steel. Now, to act as a primary structural reinforcement, what is important is that your fiber should be able to transfer bending moment and shear loads, which, for example, glass fiber cannot do. Microplastic fibers cannot do. So they are not structural reinforcement. What they help you is with plastic shrinkage. What are the governing factors for selection of right fiber? High tensile strength. It should have proper anchorage and high modulus of elasticity than hardened concrete. Glass fiber is a good product to use, trying to reduce plastic shrinkage or crazing, like the cobweb sort of patterns that you see on the floor. You can reduce, not eliminate, but reduce them by using glass fibers. A very important slide, design load. How do you specify your load? This is a very common way to specify, like 5 tons per square meter or 7 tons per square meter. The first picture is actually what represents 5 tons per square meters or 7 tons. But how many of our floors are exposed to that sort of a loading? The loads that we see are actually something like this. You have racking point loads, you have a dynamic MHE load, and what is also important, that's a second factor load, when the MHE is close to the rack. Then you have the MHE point load and the rack point load very close by. You have to design. A UDL design is very different from a point load design. I'll actually go through a case study of one of our floors that we built, very interesting. And then you can have situations where you have line loads, coils, paper rolls, etc. Okay, so we did a floor near Delhi. It was a 150 thick slab, 8 mm 200 center to center, designed for 5 metric ton per square meters and 4 metric ton point load. Now actual load was, so they called me at the site, there were cracks in the floor. They said why this has happened. Actual point load was about 6 metric tons, and this is how they calculated 5 metric tons. They took 4 point loads, they multiplied by 4, they calculated the area, length into breadth. So 4 into P divided by L into B is less than 5 metric ton per square meters. This is not how design works. You cannot take 4 point loads, take the area and divide that by the area. That is not UDL. UDL is like 1 meter is like uniformly distributed to the 5. So what we saw was, cracks running right between the rack legs. And interestingly, wherever we had a socket running between, we did not see a crack because the crack followed the socket. So this is this is actually what I realized was this is a very common way of calculating. So this is what people are doing. This is how they're calculating UDL. They're converting point load to UDL like this. Okay, now we look at very heavy load situations where you have ASRS or clad rack. ASRS is automatic storage and retrieval systems. These are very, very dense racking. Land is getting expensive. Labor shortage is a serious problem. So people are opting for storages that are taller and compact. So a dense storage. What that leads to is the typical height is about 24 to 30 meters. This is actually a project we did in Perundurai. This is a 30-meter high building. You can see the scale. The guys are looking so tiny, and look at the height of the building. This is actually ASRS. This was designed for a 22-ton point load. So the situation you have is you have very high point loads. You also have to consider seismic loads, earthquake. You also have to account for wind loads. And there are concentrated loading where bracing towers are located. So this is a very, very critical design. Your design has to be done absolutely perfectly in these sort of situations. Okay, a very interesting picture, floor levelness and flatness. I know people don't like to see this. People hate seeing water, but even if you pour water on a glass top, the water's gonna stay. This is actually a project we did in Hyderabad. This is a third-party certified FM2 special floors. It is kind of between FM1 and FM2 floor. Considered a very, very flat floor, but even a very, very flat floor, even a DM1 floor will have water. A 0-0 floor, sorry to say, but does not exist in reality. There's gonna be some. But what you need to understand is why seeing this water is a problem. Why do we talk about flatness and levelness? Look at this picture. Sir very beautifully actually explained this earlier. A 2.5 mm deflection variance at the base in the floor at a height of about 10 meter leads to about a 20 mm static lean. In certain situations, it cannot be a problem. In several, it can be a problem. This is the basis of defining levelness and flatness. Flatness is not related to seeing how much water is standing on your floor. You should not be taking a coin and putting and harassing us. Why, this 5 rupee coin or a 2 rupee coin is kind of, getting submerged. as long as your survey is passing, as long as you're within the limits. If you've defined your flatness properly based on your functional usage, you will be fine. So what is very important to know is a floor built with a certain surface regularity may not be suited for another purpose. You might come to me and say, I'll pay you a fortune, just give me like a 1 mm floor. I can give you 1 mm floor. That is how we build DM floors. But then if you're using a DM floor to run your factory, your floor is going to be in very bad shape after 6 months, because a DM floor has a construction joint every 4 meter that we cannot protect with an armor joint even if we want to, because that is how a DM floor is constructed. Every 4 meters a construction joint which cannot be protected. That construction joint goes below the racks, so we do not protect it. So even if you use a DM, even if we build a DM1 floor for you and you're using it as an FM2 floor, your floor is going to be in a terrible condition within 1 year. Secondly, if you again specifying, you have to specify it very carefully, because in future if your usage changes, you'll have to spend a lot in rectifying. But if you don't know what you're going to be using for a general purpose floor, an FM2 is a very good specification to use. Just a table. So what you see here is a MHE that can move randomly, that can move freely. FM actually, so FM actually means free movement, where your material handling equipment can move freely, can move randomly. Think of it as your two-wheeler, a bike. It can move anywhere, right? So this guy can turn around, pick the material from there, shift it here. It can do anything. It's just free to move. So an FM1 you need when your racking height is more than 13 meters. If your rack height is between 8 and 13, you need FM2. If your rack height is 4 to 8, you need FM3 and FM4. This is what FM means. FM does not mean M30 grade. FM does not mean steel fiber. FM means this, because there's a lot of misunderstanding in what FM actually means. This is what FM, that's it. This is what it means. And then we have defined movement floors. This is again a project that we did in Coimbatore. So this guy can only move in this axis. So there is, if you can see that small, circle where the rack starts, that is actually a magnet. That magnet locks this VNA truck into position. Even if there is no space, first of all, right? Where will it move? It can only go in, it can only go out. These are defined movement floors. They are built to a very, very tight tolerance, 1.3 mm, 2 mm, 2.5 mm. Again, over 13 meters DM1, between 8 to 13 meters DM2, up to 8 meters DM3. I'll just go back to the previous slide just to give you a sense of so a FM2 floor allows you about 6.5 mm variation in a 3 meter grid. So you take survey every 3 meters, it allows a 6.5 mm variation in level between those 2 points. Finally, so this is the cutting edge of our industry. We are, as flooring industry, are trying to figure out how robotics floors should be, because the guidelines or our understanding of flooring that we have right now is insufficient for robotics, because robotics needs very good bidirectional flatness. It basically needs a super flat floor in both the directions. So what we know very well to do is to give a very good flatness levelness in one direction. But what robotics guys need is this direction and also this direction. So that is something that we're trying to, as an industry, still kind of, getting our hands on. The other thing is rapid acceleration and deceleration demands a rough surface, because these guys, this is actually a project we did in Pune for a robotics company with their R&D facility. These guys accelerate and decelerate at a very rapid speed or a rate. So you need some sort of traction from the floor, right? Your floor needs some sort of roughness. But the nature of concrete floor, a good concrete floor is, the more you use it, the more it smoothens. So the more they use their robots on the floor, they smoothen, and then they have to slow their speeds because they cannot accelerate and decelerate. So this is a challenge that we are kind of grappling with right now. And so then it's never ending, right? Then there's you can design for abrasion resistance, chemical resistance, slip resistance, impact resistance, thermal resistance. This is a foundry project again we did in Coimbatore. I've chosen a lot of Coimbatore pictures. The floor this is a shakeout area. Floor was failing because of thermal impact, as well as the impact of just the stuff being dropped on the floor. We just replaced it with the metal floor and it's working really well. Okay, so it's very important for site practitioners like me and designers like consultants to work together. You know, we can, this is the flooring is like an elephant. We're trying to grapple it or understand it in our own limited ways. So we need to have a holistic approach. We both of us can come together because both of us have a lot of value to add, and ultimately the client can benefit. And that is the beauty. You know, we have builder association and a consulting association sitting here together, which I think I'm seeing for the first time actually. So the strength of a concrete technologist or a consultant in architecture is architect is theory and best practices. They know this very well. Somebody like me understands site conditions and user requirements. So we can actually marry this and have a very good end product for the client. Final section, joints, very, very important. We'll understand construction joints, go over armored joints, talk about socket joints, sealants, and finally end it with jointless and seamless floors. Okay, so what is a construction joint, first of all? So this is like a 100 meter by 100 meter floor, 10,000 square meters. All the blue lines that you're seeing is the construction joint. That is, so there are 16 panels. This floor, if we would do it with a laser screed, we would do it in 16 parts. All the blue lines that you're seeing are the construction joints. All the black lines that you're seeing are the sockets, the grooves that we cut. All the red lines that you're seeing is the isolation, wall isolation that we do. So I'll talk, so blue lines is what we are going to talk about now. So this is a construction joint. You can see the condition, very commonly seen at sites. What are the three key elements of a construction joint? Edge protection. You know, edges are completely broken. Load transfer. I think this is done fairly well with load transfer because there must be some sort of dowels. So, and joint opening. So the more shrinkage in the concrete, the more the joint is going to open, the more it is going to get damaged. So you can control this at your concrete mix design stage. Okay, now Ganesh is going to talk about equipment. So I'll just steal one slide, one idea from his deck of slides. So what is the real utility of a laser screed? All of us are kind of hardwired to think that a laser screed is going to give 0-0 level, laser driven and everything. No, that is not the main purpose of a laser screed. What a laser screed does is actually give you wide panels. So if you look at, this is a 50 by 50 meter panel. If you do it with a conventional method, use a truss screed or a screed vibrator, you're doing in panels, right? You end up having 550 meters of construction joints. The white lines that you see are the construction joints. Same 50 by 50, you complete it in 4 days, do 25 or 25 meter panels, you end up with 100 meters of construction joint. So your first line of defense against your battle with joints is reduce them. By just changing your equipment, see, your concrete is same, your design remains the same, your steel or steel fiber remains the same, hardener remains the same, labor remains the same. Just by changing your equipment, you are able to reduce the joints by 80%. That's a huge saving or protecting. You just get rid of 80% of those. And now what do you do with the remaining 20%? You actually just use an armored joint. Armored joint is a steel system that stays in the concrete. It protects the edge. So if you look at this, the black rectangles that you're seeing is actually a steel plate that protects the edge of that concrete panel. The blue line that you're seeing is actually the dowel that you see in yellow in the photograph. So the yellow part takes care of the load transfer, and the steel section that you're seeing on the top takes care of taking any hits from the MHEs. So your hit is now being taken by steel and not by concrete. So that is how your concrete is protected. And then this joint, you see a very thin line running between those two strips, right? These are two strips that will open up. So that is where, if you're dealing with this in a situation where the concrete shrinkage is very high, where the sand is very fine, what do? You actually reduce your panel size, because your panel to panel shrinkage will reduce. This joint will open lesser. But as long as you have an armored joint opening of about 10-12 mm, you're still fine. What you should never do is just install dowels, put your formwork and not armor it. Because what is a very common way of doing is you fix plate dowels, put your shuttering, next day remove the shuttering and you cut a groove on top of that line. That is very, very high chance that it's gonna deteriorate. This is something that you should avoid. I've said this enough times that concrete, you should minimize shrinkage. So just to summarize, first you minimize the construction joints by using wide panel system. Second thing is never just install dowels, use armored joints, and then minimize shrinkage with a proper mix design. Fairly simple. We cut grooves at every 4 meters because concrete has a tendency to shrink. If we do not cut grooves, it'll randomly shrink. And this is actually a photograph where if you can see the socket, the crack has kind of gone, traveled below, and that in the red is a picture showing that. So all sockets actually have a crack traveling through and through. So let us say you have a 10,000 square meter floor plate. You'll have typically about 5,000 running meters of socket. So you actually have 5,000 running meters of cracks already. So if you see like a 10 or 20 meter of crack in the floor, random cracking, you should not panic because there's already 5,000 running meters of crack there, quite nicely hidden. So what is important is timing. You should do your groove cuts between 24 and 48 hours, and the depth should be 1/3 to 1/4. Isolation joints, again, we want to isolate the concrete from all the building elements. We want the concrete to be able to shrink independent of everything else. We typically do a 20 mm foam board at the pedestals and a 10 mm at the walls. What I have seen is like we give shear connectors in these slabs. Here, people also leave steels horizontally from the plinth beam or the walls. We actually go and get them cut. You should not have any connection between any building element and the floor element, because what you're doing is you're creating restraint. That restraint is going to result in cracking. So those things you should avoid. You should use a hard board or a soft board. Hard boards are commonly specified, but actually you should be using a soft board. What you see in picture is a soft board. Because just imagine you have a column and concrete is shrinking from all sides. It is exerting a lot of pressure on the concrete, right? A softer board will kind of give that extra cushion. A harder board will give it that, reverse feedback, and your chance of cracking increases. Always specify softer boards. Joint sealants, we have polysulfide, PU, epoxy PU. Polysulfides are good only for road. They are too flexible and they do not have that strength to hold the MHE traffic in a floor. PU sealant is very good. Let's say you just build the floor. Just seal it with a PU sealant because it has the right amount of flexibility to allow the concrete to shrink and also the strength to protect the edge. And then after 12 months, wherever you have MHE movement or wherever you have traffic, you should remove the PU sealant and use it with an epoxy PU sealant. You should actually, that has a shore hardness of about 70 to 80. You should not, and you should also fill the armored joints. So your armored joints will open after 12 months, about 10-12 mm. Fill that also with an epoxy PU sealant. You should avoid using an epoxy PU sealant right immediately after construction because it is rigid. It does not have flexibility. So what will happen is when the concrete is shrinking, you will see the sealant itself cracking. You will see crack in the sealant, which you do not want. Very good to use it after 12 months. You just need to do it like once, and you usually don't need. And I think I'll just have a couple of more. So now this is like, this is like the rocket science of flooring. If you're fed up of joints, this is what you can do. You can go for a jointless floor. You see there are no sockets. You can actually take it. So what you have is an armored joint. If you look at the column line, there's a line running in the floor. That's an armored joint. So in a jointless floor, you still have armored joints. In a seamless floor, you do not even have armored joints. All your armored joints are replaced by tight joints. It's like a hairline which barely deteriorates over time. So this is like, it's a very good solution for cold storages. This is a project we did in Mumbai. That is about a 3 lakh square foot project we did near Delhi. Very good for cold storage because at -25, if any floor damage happens in the floor, you cannot go in and repair. I am not aware of at least materials that work in that, and how will people work in -25? Seamless is actually a very good solution for cold storages. Well, something's off here. I'll just ignore this slide. Okay, so just visualizing the impact of a jointless floor. Use the picture that I used before. Left side, you have 400 meters of isolation joints, that is a red line. About 600 meters of armored construction joints, that is a blue line. And 4,000 running meters of sockets. Now, if you go for a jointless floor, your 4,000 running meters of sockets suddenly become 0. I mean, you can see the difference, the significant difference in the number of joints by just shifting to jointless. And if from jointless, if you decide to take a step to seamless, you also do away with these remaining 600 meters of armored joints. So I think this is it. Thank you for your time and patience.